Hola amigos, so now let's move on to our next topic, that is relation between CD0 and CDI, which is at 450 page number of chapter 6, Elements of Aeronautics of book Introduction to Flight by J.D. Anderson. And these graphs which we drew earlier in our lecture, we will be referring these graphs, and I have made a little bit more about this power required and range, and we will be looking at these graphs as well. So let's start with relation between CD0 and CDI. And why we are finding the relation between CD0 and CDI is because we know from Dracula that coefficient of drag CD is equal to CD0 plus CDI. Okay, so Dracula curve is actually this, which is varying with CL. CD shows a variation of parabolic nature with minimum drag for preliminary design only we are talking about, and the minimum coefficient of drag, zero lift drag, is CD0, and CDI is this parabolic variation, and total CD or coefficient of drag for total aircraft is CD0 plus CDI. And we have learned earlier that for thrust required to be minimum, which is this graph, okay, the black graph over here is for thrust required, and this is the power required curve, which is having a more curvature as compared to thrust required because it varies with v square. With velocity we are seeing the variation, and power required is varying with v cube, and these are the minimum points for power required and thrust required minimum respectively. And we know for thrust required to be minimum, we found that it is at a point at which CL by CD ratio is maximum, okay, and for power required to be minimum, we found that it is minimum at design point at which CL raised to power 3 by 2 by CD is maximum. Okay, if you don't remember, I would request you to please go through earlier videos or refer the textbook, and from there you will also get to know we compute the velocities at those design points, and then we look at these velocities so that the pilot fly at these velocity, and it should make our aircraft fly with minimum power required or thrust required minimum, so that it would cover maximum range or maximum endurance with respect to the type of engine installed on the airplane. Okay, so now moving on to the relation between CD0 and CDI, we have thrust required minimum, as I said, is at CL by CD max. How did we know that thrust required is equal to drag, and we multiplied by lift and divided by lift, and for steady level flight we know thrust is equal to drag, which is over here, and multiplying and divide by lift and substituting lift equal to weight. For a level flight we know lift is equal to weight, and from there we got when thrust required is minimum, then L by D is maximum. Okay, drag was above and we brought it down in the denominator, and with L by D maximum we get thrust required minimum, and the corresponding velocity at thrust required minimum is given by this point. Thrust required minimum is at this point, and the corresponding velocity is this, and here we see that CL by CD will be maximum. Okay, and at what value of CL, because if you see the velocity formula, okay, here we have for lift equal to weight, actually we are only talking about steady and level flight, so lift will be equal to weight, and based on that, from aerodynamic relation, velocity is inversely proportional to CL. So we know the value of CL, but the pilot only talk in terms of velocity at which the aircraft will be flying. The pilot does not know anything about CL, coefficient of lift, or angle of attack, so he only speak about the velocity at a given moment or at a given altitude. So its flight path, the aircraft flight path is fixed, and based on that its velocity at those altitudes are fixed, and by fixed it necessarily does not mean that it will fly at that particular velocity, because based on the wind speed and all those calculations, relative speed should be the same. Okay, relative speed should be that speed only, that if say 100 km per hour was the speed of aircraft, then it should fly at 100 km per hour to maintain a level flight. Okay, so but it is not necessary that it should not be flying at 120 or 130. It may fly, but it will show a little degradation in the performance of the aircraft, a little degradation, which may affect the overall range or endurance of the aircraft. So now let's get back to the relation between CD0 and CDI. That is, here we know for thrust required to be minimum, L by D should be maximum, and lift and drag are only indifferent with respect to their coefficients. That is, drag is half rho v square as CD, lift is half rho v square as CL. So other terms cancel out, and CL by CD max is left. And we know now that velocity is varying with CL, okay, but pilot does not know about CL. So ultimately pilot has to know about what velocity an aircraft should be flying. Okay, so we know from aerodynamics what is CL. It is the beforehand data given by the aerodynamicists, and from this knowledge we derive CD0 and CDI relation. That is, for CL by CD to be maximum, we are finding a point that is at what CL by CD is maximum, and with it, or say with respect to coefficient of lift of aircraft, what is that coefficient of lift of aircraft for which CL by CD is maximum, and for quantity that is in dy by dx to be maximum, for a quantity y to be maximum with respect to another variable x, it should be equal to 0. Its derivative should be equal to 0, or even if we want to find the minimum, then dy by dx of the given parameter should be 0. Okay, so y is always a dependent variable and x is an independent variable, so dy by dx is equal to 0, and upon solving this by substituting CD is equal to CD0 plus CDI, and we know CD0 is CD is equal to CD0 plus KCL square, and upon solving this derivative, we get to know that CD0 is equal to CL square upon pi e aspect ratio, and 1 by pi e aspect ratio is the value of K, which I talked about here. That is, CD is equal to CD0 plus CDI, and CDI is equal to KCL square, and K is 1 by pi e aspect ratio. And from here, we can deduce that the coefficient of drag for a non-lifting part of the airplane is equal to the coefficient of drag for lifting part of the airplane. Okay, it's because the lift is inducing drag, and from there, from this calculation, we get to know that thrust required will be minimum at CL by CD max, and from this we get to know that when the coefficient of drag for zero lift is equal to the coefficient of drag for the lift producing elements, then the aircraft will be performing at minimum thrust required, or it will be flying at minimum thrust required, where CL by CD is maximum. So from this we can say CL by CD is maximum when CL is substituted in terms of CD0 and CD is also substituted in terms of CD0, because CD0 is always a fixed parameter, you can say, for a given velocity, and CD0 is expressed in terms of CL by using this formula, and we know that CD is equal to CD0 plus CDI. So CD is equal to CD0 plus CDI, these both are equal, therefore we have 2 times CD0 over here, and here we have CL which is equal to CD0 pi E aspect ratio. So here we will be having 1 by 2 because we have this square over here, so it should be 1 by 2 CL, only this part I'm talking about. Numerator should be 1 by 2. Okay, denominator is 2 times CD0 and numerator is in the under root, only numerator is in the under root, which is CL. Okay, CL is equal to under root CD0 pi E aspect ratio. So CL by CD value can be derived like this. If we know CD0, then we can find CL and CD. Now moving on to the power required, and from the graph let's see again that for thrust required we have this graph, and it is minimum at this point, and at this point we have CL by CD max, and CL by CD is maximum when CD0 is equal to CDI. Okay, so we are seeing from this graph actually that we know that from drag polar curve CD varies with CL like this, and from this thrust required curve and power required curve we know these lines, these dashed lines, are the thrust required for zero lift, and this is thrust required for lifting parts of the airplane. Okay, so this is the thrust required for zero lift, which is intersecting at this point with the thrust required for the lifting parts, and it is equal to the CD0, and it is CD0 equal to CDI point. Okay, so they are intersecting at this point, which is CD0 equal to CDI, and it corresponds to thrust minimum point, and at that point we have velocity corresponding to thrust required minimum. Similarly we have for power required minimum, and it is a little bit towards the left. Okay, and similarly we have for this range maximum, whose graph is not there, but the corresponding CD0 and CDI relation is given by this dotted line. We will be exploring this in just a while. So for power required minimum we have power required equals thrust required into velocity, and we know power required is given by this formula when thrust required is substituted in terms of drag, or say thrust required is substituted in this form, and velocity is then given by this formula, V infinity is substituted by this formula, and then we get power required as in terms of CL raised to power 3 by 2 divided by CD, which means that power required is inversely proportional to CL raised to power 3 by 2 by CD, and power required will be minimum when this aerodynamic ratio, which is actually the design requirement for aircraft to perform optimally, that is, it will perform optimally when it will be flying at minimum power required, so that it will consume the fuel in very less quantity, and that will make our aircraft perform economically. And based on this we can say power required will be minimum when CL raised to power 3 by 2 by CD will be maximum. And similar to the thrust required relation, thrust required minimum relation for CL by CD max, we computed CD0 equal to CDI, and similarly we will find here for CL raised to power 3 by 2 by CD max for a given CL, we deduce that CD0 will be equal to CDI by 3, which means CDI is 3 times of CD0, and at this point, or at this aerodynamic relation, we find that power required will be minimum. So from the graph let's see where it is. We have this power required graph, and power required is minimum at this point. Okay, and at this point if we bring it down, here we have this CDI and this CD0, and this is the point at which power required minimum is getting down, and at this point CDI is this and CD0 is this. Okay, and CDI is 3 times of CD0, this CDI is 3 times of CD0, which is giving us power required minimum, and corresponding velocity is given by this.